Today on How It's Made. Cast iron cookware. Dishing the dirt on pots and pans. Biodiesel. You really can run your car on chip fat. Clothes hangers. Making creases a thing of the past. And stone wool insulation. It's like a jumper for your house. But first, cast iron cookware is renowned for its superior ability to retain heat and diffuse it evenly. However, bare cast iron requires regular oiling to ward off rust. Not so with enamelled cast iron. This makes the cookware entirely maintenance-free, apart from the washing up, of course. Since 1925, this French company has been producing enamelled cast iron cookware. Its high-end products are renowned for their thin walls, which makes it the most lightweight cast iron cookware available. The secret? Mineral levels in the iron recipe. At the foundry, they begin with pig iron, which has a high carbon content. They then melt in a calculated amount of steel to further boost the carbon level. A furnace heats the metals to 1,520 degrees Celsius, liquefying them in just 45 minutes. Workers add a powdered chemical to agglomerate the natural impurities in the iron, then scoop those bonded impurities out. Meanwhile, workers mount a two-part mold template onto a machine, which produces the sand molds with which they'll cast the cookware. The machine injects into the templates a sand mix that contains clay, water, and proprietary ingredients to make the sand compact. Compaction is critical because just one single grain of sand displacing from the mold would produce a flaw on the cookware. It's essential that the pouring temperature be precise and consistent. So they transfer the iron from the furnace to a temperature maintenance oven. From there, they pour the molten metal through a mere 3 mm gap between the mold halves. The process is entirely automated because the pouring angle and speed are critical. The molten iron cools and solidifies in 20 minutes. Then the molds drop onto a vibrating mesh conveyor. The shaking releases the cast cookware from the mold, along with the metal that's solidified in the flow channels leading to the mold cavity. The cookware moves into a closed chamber, where a high-pressure gun blasts the surface with steel balls to remove all remaining grains of sand. At this stage, the cookware has rough excess metal where the two parts of the mold met. So now workers smooth away these burrs, using a grinding wheel on the outside and a grinding pen in the tight spots. The cookware is now ready for enamelling. First, a machine blasts the entire piece with steel grits, making the surface texture uniform so the enamel will adhere evenly. The first coat of enamel is to protect the cast iron and prevent it from rusting. Enamel is a form of glass. However, this enamel is engineered to be flexible because metal cookware naturally expands as it heats and contracts as it cools. After a trip through a dryer, the enamel goes into an oven at 850 degrees Celsius for about 45 minutes. During this firing, the hair-thin enamel coating becomes translucent. The second coat of enamel completely seals the porous surface. It's made of some 20 components, including enamel chips, pieces of clear glass, and pigment powders for colour. An automated spray system coats the inside first. Workers wipe the edge to prevent the piece from sticking to the conveyor. Then the handle, because they'll paint that a different colour. They spray the handle manually. Then the automated system coats the rest. The iron recipe contains a high level of the mineral silicate, which helps the enamel adhere well. Once again, the cookware goes through the dryer. Then into the oven at 850 degrees Celsius for about 45 minutes to vitrify the enamel. Once the cookware cools, it undergoes a final visual inspection, the last of 30 quality control checks throughout the production process. Enameled cast iron cookware lasts generations because it doesn't warp over time. Fantastic! Biodiesel is a more eco-friendly diesel fuel that's made from vegetable oil or animal fat. Unlike regular diesel and petrol, producing biodiesel doesn't require petroleum oil. Instead, the raw materials are locally available and can be recycled from waste. If your car has a diesel engine, it can run on biodiesel fuel, usually without requiring any modifications. While biodiesel and petroleum diesel are similar in energy efficiency and fuel economy, biodiesel is more eco-friendly. For starters, it can be made from what would otherwise have been waste. For example, from vegetable oil from the kitchen of your local takeaway. The restaurant simply discards its used fryer oil in a receptacle out back. Every few days, a vacuum truck comes to collect it. In its current state, the oil contains water and food particles, making it unusable for biodiesel production. So the truck transports it to a filtering plant. There they pump the oil into a holding tank, then heat it up to draw out the water. Once they drain the water, the oil is ready to enter a multi-stage filtering process. First, the oil goes through a vibrating sieve, which strains out the larger pieces of debris. After this first filtering, the oil is already visibly cleaner. Next, it passes through a second vibrating sieve. This one has a finer mesh in order to catch smaller particles of debris. After this second stage, the oil looks clean, but it still contains microscopic debris. So it enters the third and final filtering stage, passing through 20 ultra-fine filter cloths, which trap any particles larger than 1 micron in size. A micron is about 80 times smaller than the width of a human hair. The captured debris leaves a muddy residue on the filters. That vegetable oil, which once deep-fried potatoes, is now ready to cook up some diesel fuel. Another source of oil for making biodiesel is beef tallow, oil derived from cow fat. Biodiesel producers typically buy tallow from facilities like this one, which specialize in cleaning cow hides for leather tanneries. Sharp revolving blades shear off the fat from the back of the hide. The fat drops onto a conveyor, which moves it into a steam injection cook tank. The tank heats the fat to a gentle boil, extracting the oil. Everything else leaves the tank and drops into a waste container. The oil moves onward, passing through a two-stage filtration process. Whether the raw material is vegetable oil or beef tallow, the biodiesel producers refer to this main ingredient as feedstock. When the feedstock arrives at the biodiesel plant, it goes into a holding tank until production time. This demonstration illustrates the production recipe. They take the feedstock and combine it with methanol, a type of wood alcohol, as well as a catalyst, which triggers a chemical reaction. The processing unit mixes everything thoroughly while applying heat and pressure. The resulting chemical reaction produces a harmless byproduct, glycerine, a common ingredient in soaps and cosmetics. Processing consumes much of the methanol. Then they remove even more, leaving just a tiny percentage of it in the finished biodiesel. To ensure their fuel meets international regulatory standards, the plant's quality control lab tests samples from each production run. In this flammability test, they heat the fuel to 135 degrees Celsius, then apply a flame to see whether the gases ignite. If they do, they have to remove more methanol to make the fuel safe. If they don't ignite, the fuel meets international safety standards. Biodiesel costs more at the pump, but emits significantly less carbon dioxide and monoxide, and 85% fewer cancer-causing agents into the air we breathe. So in one respect, chips can be good for you. Coming up, thanks to the clothes hanger, crumpled garments are on the decrease. And stone wool, a rock-hard insulation. See you after the break. Someone, historians don't know exactly who, invented the clothes hanger, a hanging device shaped like human shoulders. Since the mid-19th century, hundreds of inventors have patented various shaped hangers, many of which are still being produced today. This Czech company makes wooden hangers in several styles. It uses beech, a hard and durable type of wood. The damp logs air dry outdoors for 7 months, then go into a kiln for 3 to 4 weeks. Drying the wood is critical, otherwise the hangers would expand and contract with temperature changes and eventually crack. Workers first use a bandsaw to slice the logs into 6 centimeter thick planks. Then they put each plank through a broaching machine. Inside, a toothed blade planes the wood, rendering the top and bottom surfaces level and smooth. The next stop is a grinding machine, which contains abrasive belts. Workers feed the planks into the machine one at a time. As each plank passes through, the belts above it sand the top silky smooth. When the plank exits the machine, workers flip it and refeed it to smooth the other side. An automated saw cuts each plank in half and trims the halves to a specific dimension. The now smaller planks go into another grinding machine, which sands the sides smooth. Now the hanger shaping begins. Workers stack 10 planks and, using a circular saw, cut them to the same length, making sure the ends are at a 60-degree angle. They mount 4 planks at a time on a milling machine and cut a tongue and groove profile on the edges. They'll later connect the hanger parts by fitting the tongues into the grooves. Stacking 6 planks at a time, they trace a hanger-shaped template on the top surface, then carefully follow the trace line with a jigsaw. Each plank is now roughly shaped into half a hanger, which they call a lamella. This particular hanger is designed for dresses, so they'll mill a groove in the shoulder of each lamella for garment straps. Then an automated milling machine refines and finalizes the hanger shape, smoothing the rough-cut wood in the process. Next, with strong cabinet maker's glue, they coat the tongues and grooves of the 2 lamellas, then fit them together on a press. They let the glue dry for a day, then saw the point off the top. This creates a flat area into which to insert the hanger's hook. There's already a hole for it there, made when they milled the tongue and groove profile. Next, they sand the joint to remove excess glue and smooth out any nicks or tears in the wood. Then they round the angular joint. To seal and protect the wood, they now spray the entire surface with varnish. When it dries, they do a rough sanding, then apply a second coat and let that dry. Many customers want their logo printed on the hangers they order. The printing machine coats a logo embossed rubber pad with ink. A sponge dabs the pad, then stamps the logo onto the hanger. Finally, the hanger's iron hook. It's either nickel-plated for a silver tone or brass-plated for a gold tone. Workers position the hook. Then a press rams it into the wood 1 centimetre deep. The hook has screw-like threads at the base which grab and lock into the surrounding wood. For certain models, the factory stains or paints the wood prior to varnishing it. Apparently, some people like their clothes hangers to make a fashion statement too. Personally, I wouldn't get hung up about it. 150 years ago, an erupting volcano led to the invention of stone wool insulation. It was observed that volcanic lava could be whipped into woolly tufts by prevailing winds. Soon this was being replicated in factories to produce stone wool for insulation. Shaped into slabs, stone wool insulation can be tucked snugly between the studs of a framed wall. It acts as both a thermal and acoustic insulator. And here's the soundproofing proof. In this demonstration, an activated alarm goes into a box lined with stone wool. When the lid is closed, the sound is contained. And when it's lifted again, the annoying sound is back. Stone wool is made from basalt rock and slag, recycled from the steel industry. The process is fueled by coke, which is a form of coal. Basalt rock is solidified lava, formed when molten rock cooled quickly underground. After the rock has been partially crushed at the quarry, a loader scoops it onto a screen to separate the bigger pieces from the fine particles. The particles will be processed into briquettes, which can be used in the production of stone wool, along with the bigger pieces of rock. The rock and briquettes, along with the steel slag, melt into lava in a furnace. Temperatures reach 1,500 degrees Celsius, as hot as a volcano. A spinning machine whips the lava into thin strands of stone wool, in a process that's like making candy floss. The strands form tufts, and a little binding solution holds them together. A spray of oil adds water repellents. Now a fleecy web, the stone wool rides a conveyor to the factory's upper level, where it spills into a huge pendulum device. The pendulum swings to and fro to layer the stone wool in a zigzag pattern. The number of layers varies depending on the kind of insulation being made. The now layered stone wool travels between rollers, which compress it substantially, adding density to the wool. Automated pushers tuck in the pack on each side as the wool enters a long oven. The heat cures the binder that was applied earlier, allowing the compressed fibers to hold their shape. The now tighter pack exits through a cooling zone and travels under a roller which squeezes it to make the fibers more flexible. Circular blades then slice the moving mass of stone wool lengthwise. A branding tool burns the R value, its measure of thermal resistance, onto the surface of the insulation as it moves forward. Robotic arms swing back and forth to slice the insulation to its final dimensions. Instead of sharp steel blades, these robots use high-pressure water jets to make their cuts. The jets do a precise job without generating dust or waste. And the stone wool doesn't absorb the water from the jets. Along with the oil added to the fibers during the spinning, the sheer density of the wool makes it moisture-resistant. To demonstrate the stone wool's water-repellent qualities, they pour water directly onto the surface. There's no absorption. The water just runs off. And in this routine test, a worker torches the wool, and it doesn't catch fire. Stone wool can withstand temperatures of almost 1,200 degrees Celsius due to its natural properties. It's even cool to the touch on the other side. Once it's passed several quality control tests, the insulation heads for the packaging line. Grippers pull on a roll of plastic tube packaging, and hot jaws cut and seal one end to form an open bag. Mechanical fingers hold the other end open as machinery slides it over a metal spout. A compressed stack of insulation is pushed into the spout. The spout expands and the insulation is released into the bag. The spout then retracts and the process is repeated. Machinery heat seals the open end. From a pile of basalt rock and recycled steel slag to a bag full of insulation, it's been a wild and woolly ride.